equating everything we already know to everything we don't know yet, okay? So there are two kind of big columns. So there's like the quantity stuff over on the far left. And then the next thing over is it's labeled translational. So translational is all the motion that we've studied for the last however many months we've been together since August. We understand translational motion really well. You know about displacement, acceleration, you know about kinetic energy, you know all that stuff about translational motion. But now in unit 7, all in one unit, so we did 6 units already, right? 6 units of this happy-go-lucky translational motion stuff. And now in one unit, in unit 7, we're going to put all of rotational motion. Okay, we started already, but we haven't gotten there. We haven't gotten very far. And this is where we're going to kind of organize ourselves about. Okay, so let's start with the stuff we know. You know what displacement is, right? What letter do we use to mark displacement usually? X? X or delta X maybe, depending on, right? Like, so position is X, and so displacement is change in position. What units do we use to measure? Not feet, not nanocentimeters. Base unit is the meter, right? What's the definition of velocity, you guys? Don't overthink it. Yeah, don't overthink it. Delta X over T, change of position over time, right? Units for velocity, translational velocity, what are the units? Yeah. And acceleration, we defined that one as well. This was like October, or not October, August. Yeah. Units are? Good for us. Okay, so that was August. Now we're here in February. The same stuff, but instead of talking about translation, so translation means in a straight line, right? Rotation means in a circle. Instead of measuring things in meters or in nanocentimeters or whatever, okay, now we're going around in a circle. How are we going to measure a displacement in rotation? We're going to use radians. We are not using degrees. Even if you like, I heart degrees, like whatever, we're going to use radians. And it's important. Nope, we just write RAD. Rad. And the funny thing about radians, and I'm glad you asked, is that radians, it's just a ratio. You guys know this from math. We're going to go over it again tomorrow, okay? But we're not gonna spend a lot of time on it right now because we don't have a lot of time to spend on it. But I just want you to know that it's just a ratio. There's really no big deal, okay? Theta is generally measured as an angle counterclockwise, okay, from the x-axis. Okay. Easy peasy, we got this. And again, we'll go through that a little bit more tomorrow. I want to get all these pounded out here though. Just like velocity, translational velocity is change in position over time. Same here. It's the change in theta over time. That's all it is. No big deal. Delta theta over t. Okay. This thing is known as angular velocity. Rotational velocity. It can also be known as, and this one's a little bit funny, again, we'll go over this tomorrow, but I want to make sure we have it written down, angular frequency. You've met this one before when we talked about it as angular frequency. What is it? It is omega. Good memory. Omega. And the units are radians per second. If you remember that radians aren't really anything, then this is just 1 over seconds, which is first, which is why we call it angular frequency. Yeah. And then we can take it one step further, right? We can say that just like acceleration is change in translational velocity divided by time, we've got a similar thing here that's going to be the change in omega divided by time. Okay. This is our angular acceleration. And the thing, nope, it's not though. That's the thing, it's different. It's different. We'll get there soon, but we're not there yet. Angular acceleration is just speeding up or slowing down as you're going in a circle, which is different than centrifugal acceleration. Okay? You're going to notice a trend with rotation, and that is that we're using Greek letters for all of them. Angular acceleration is going to be marked with the letter alpha. You got it. And the units for it, my friends? The units are? You got it. We're going to write down a couple of things. There's some space at the bottom of your page that you can write this on, or you can write on the back. I'm going to write it over here just so that I can kind of reference some things here, because I promised you yesterday that we would talk a little bit about radians and about angular frequency, and I want to do that. I didn't want to, not be truthful. I know that some of you have a loving relationship with the measure of radians. Some of you do not. And I want to make sure that we all feel good about them. So I'm going to tell you a little story, okay? It's a little story about when I used to teach math way back in Des Moines, way back, right? And I used to teach about radians to my eighth graders that were taking geometry. And the best way to get eighth graders to engage with mathematics, I found, is to engage them with candy. Okay, and so what I would do is I brought Smarties. Do you guys remember what Smarties are? Those little circular candies. Sometimes we did Smarties, sometimes we did M&Ms. And I would give them a piece of paper, a piece of graph paper like this that had a bunch of circles on it. Okay, and then we would do this little game. And did you guys? I don't know if you guys did this game when you were in math, when you were learning about this, but now you can shake your fist at those math teachers that didn't do it. Here we go. So I'm gonna line up little Smarties along the x-axis, a radius of 3 out. And then I'm going to follow that circle up, and we actually went all the way around the circle, but I don't want to waste time doing that. And then I would go add a couple more, and then I would go up like this, and we would line up our little M&Ms like this, or our Smarties or whatever, and then we go add a couple more, and then we do the same thing, and we'd count them up. And the really interesting thing that they discovered from this, and that you probably at some point in some mathematics class discovered as well, is that the game, the reason that we love radians is that it's just a ratio. That is all that it is. The ratio of the radius, or the arc length to the radius, arc length to the radius, arc length to the radius is always the same. That's all it is. And if you do the ratio of the arc length to the radius going all the way over here, do you know what that ratio gives you? Just a little over 3. And if you do the arc length to the radius all the way around the circle, do you know how it gives you? A little bit over 6. Yeah. And if you get a ratio of 1 to 1, you get an angle that goes up like this. Anybody want to guess how many radians that is? 1. When the ratio is 1 to 1, then you get that same angle all the way through. Okay. A radian, 1, 2, 3, 1, 2, 3, goes like this. And this is 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, 6, 7, if I draw it right. All that it is, a radian, is just the ratio of arc length, or part of a circumference, divided by the radius. Okay? That's all it is. There is nothing to be scared about. Somebody in 7th hour yesterday was asking, what's the unit for radians? And there really isn't one, because it's like meters over meters or centimeters over centimeters. It doesn't matter. It's just a placeholder, because it's just a ratio. That's all it is. Okay? When you go all the way around what we would consider 180 degrees, so halfway around the circle, the ratio of arc length to radius is 3.14. And if you go all the way around, it's twice that. That's what we're talking about. Okay, so I just want to let you know that it's really not scary. Okay, because I know that for some people, it's just like there's a lot of anxiety that comes with radians. And when we do rotational motion, we deal with radians. And I don't want you to get like so anxious about it that you just like shut down and don't want to play with it anymore. Because I know that that happens. I totally get it. Does that make sense? Is that okay? It's a beautiful thing. Radians are really pretty awesome. Okay. You can also remember here, if you're trying to keep track, that 360 is equal to 2 pi radians. And we're going to use that knowledge in just a second as well for some other things. We need to know how to do those conversions now and then. The other thing that I wanted to share with you, that you might want to throw in some notes here, is about omega. We said omega yesterday was angular velocity. I also mentioned that it was angular frequency. And this, you guys, we talked about this about 2 months ago. We talked about omega when we were talking about the simple harmonic motion, bouncy, bouncy, bouncy stuff. And I introduced you to omega, and I said, just wait, we'll get there. And now we're there today. Okay? Omega is change in position divided by time. If we go all the way around a circle, how many radians is that? 2 pi of them, right? 2 pi radians. And it takes how long to do that? It takes a period. Does that make sense? A period is the time for one full revolution. So we can also write omega as 2 pi over t. Okay? Or we can write omega as 2 pi times frequency, f. And that's why we often will call it angular frequency. Because it's literally how often does it go around the whole circle? That's all it is, right? It's radians per second or a full cycle in a period. That's all it is. So the units generally when we're talking about these things are in radians per second, but sometimes we will refer to them in hertz, just because radians doesn't mean anything because it's a ratio, and then per second is just in hertz. How are we doing? So far, so good? Sweet. All right. I got one more thing here, I think, that I wanted to tell you. Is that right? Nope, we're going to do one more thing. The other thing and I'm actually going to write this one down on the bottom because I am going to insist that if you haven't written it down here, you do now, and that is converting from translational to rotational and back. Okay. We know translational stuff really well. You know it, you understand it. It's deep inside your core. Rotational is a little bit newer. We don't spend our lives, I mean, it's kind of ironic. As physics teachers, when we sit down and talk about why rotational motion stuff is so hard, we talk about it because, you know, everything that we see goes in a straight line. I was just about to say, we don't spend our life doing things in circles. Let's be honest, we're on the earth, right? The earth is doing circles all the freaking time. And the earth is going around this, like, we live in this rotational world. We just don't recognize it in that way, okay? But we can convert really easily between them, and that's really nice. So I'm going to jump back here to our definition of what an angle is. We said an angle is the arc length divided by the radius. The arc length is really just a distance. So this is really just a distance divided by the radius on the circle. So that's the part of the circumference you traveled divided by the radius. And so then we can solve that for x. We can say that the translational position or displacement, I guess I should probably write these as deltas just to be a really good kid, okay, is equal to delta theta times r. We know, that delta x over t is equal to v. Yeah, we've known that for a while. And so instead of writing v, we can write this as, oh, hold on, just make sure I'm doing this right. What did I just do? Oh, we can write that, yeah, as, sorry, I just lost my train of thought. Delta theta times r over t. Hey, what's delta theta over t? Omega. So we can also say that v is equal to omega times r. Okay. We can take it one step further. We can say that delta v over t is equal to a, which really just happens to be omega times r over t, and omega over t, or change in omega over t. Angular acceleration, what letter is that? What do we call it? That's a really good question. Alpha is what we call it, absolutely. So we can say that a is, oops, not proportional to, is equal to alpha times r. So if you're going to circle something, remember something, this is the thing to remember. Woo! We got 2 more boxes to fill in. What? VF is equal to VI plus AT. Do you agree? Can you translate that into the rotational business? Instead of V, you're going to write omega. Instead of A, you're going to write alpha. And time is time. Let's do another one. My favorite one, delta x is equal to VIT plus 1/2 AT squared. It's been a while since you played with these. They're back. Oh yeah. Delta theta is equal to omega initial times time plus 1/2 alpha times squared. Friends, now that you know all of the kinematics stuff, this is easy peasy. You got this. Okay? When you do these problems, givens, unknown, equation, substitute, solve. You got it. One more. Here it comes. VF squared equals VI squared plus 2A delta X. You translate that one. You can do it. Use the rotational variable. It's the same darn thing. What's it going to start with? It's like you could have written this down or something, Eden. What? Omega final squared is equal, what's going to be the next thing? Omega initial, right? Squared plus what? Okay, then what? Oh my gosh, and then what? Oh my gosh! Whoa, it's amazing.